So let's start lesson 15. Lesson 15, we're doing the normal distribution. We started the normal distribution in lesson 15. Remember, the biggest key takeaway from these are two things. First, well, three, I suppose. We have continuous variables. We have curves that are basically built off of histograms, but they are continuous curves, and we chunk up these curves into regions with a certain area, and that area of that region is the probability of randomly selecting something that falls in that area. Now, the normal distribution, also known as the bell curve, is a special distribution that most things that naturally happen in life become approximately or close to normal. In lesson 15, we're continuing the material that we learned at the end of lesson 14. Okay, and the normal distribution is something we're going to continue also for lessons 16 and 17. The sooner you get the important ideas of the normal distribution down, the easier this is going to be for you. So what I'm going to do is I'll cover a couple of examples from the worksheet, and then I'll have you work on a couple of examples on the worksheet. Okay. And I do want to remind you that, what I've heard from some people, an effective way that they do this class that helps them learn the material more easily is they watch the videos beforehand, then they come to class, they do the classwork, and then after class, they go back and finish the worksheet on their own. I think for a lot of you, that probably will be a more effective way to learn, so you're not getting a little bit lost. Anytime you're getting really confused on the worksheet and you're not really sure on how to do things, feel free to just wait until we're doing it in class. But make sure to find the time to finish the worksheet on your own. Okay? All right, so let's start with example 1. And this is the empirical rule. And the empirical rule is a very important concept and is really the crux of the normal curve and what makes it so special. Okay, so the probability equaling area, this is not just something for the empirical rule. This is for all continuous variables and actually discrete variables too. In example 1, we're going to use the empirical rule. And again, this is something we covered in lesson 14, but it's a good way to start because it's so important. So we're going to use the normal curve to answer the following questions. And remember that the tick marks on the curve represent one standard deviation. And if you remember from lesson 14, that is how we divide up this empirical rule. Okay, so we're going to use we're going to label the z-scores for each tick mark vertical line. Okay, and so remember the z-scores start out in the middle, that's 0. And I'm going to put a little z over here just to remind myself that we're talking about z-scores. And remember, so this right here is, this peak is the mean and the median. And the mean, we have that curly M, and the median we refer to as just a big M, regular M. Okay, so everything up here on the right side of the mean is above average, and everything here on the left side of the mean is below average. Okay, and remember these z-scores tell us a lot of important information that we can discern from and learn a lot about the variable we're going to talk about based on what its z-score is. Going up, I'm counting 1, 2, 3 standard deviations. Counting down, I'm going -1, -2, -3 standard deviations. And that's generally the order in which I always label my normal curve. I start in the middle, and I go to the right, and then I go back to the middle, and I go to the left. I don't suggest you try and start down here. You'll go crazy, and you'll be doing 3 times as much work in order to figure out this value. Normally, we do things left to right, but for this, you really do want to start in the middle, go to the right, because that's all addition, and then go back to the middle and go to the left because that's all subtraction. Now let's find the probabilities of each section. The probabilities are one of the many things we get from the empirical rule, and these are static. Anytime you're told you have a normal curve, it will always have these probabilities. I like to start in the middle. Remember, this curve is symmetric, so this is 34%, 34%, 13.5%. Again, I fill in these two, and then I go to the right doing those, and then I go back and I fill in these. This one right here is 2.35%, and this bit here is 0.15%. And I want to remind you, the z-scores don't stop at 3. They continue going you could get a z-score of 10. Z-scores beyond 10 are extremely unlikely. Z-scores around 5 you'll see occasionally, but we stop at 3 because it becomes very unlikely. Same with back here. It continues on past that -3. And these are going to be the same areas in the same order. So this is 13.5 between -1 and 2, 13.5%. This area here is 2.35%. And this really little bit that looks almost flat is 0.15%. Okay, so now we're going to find the mean standard deviation. So remember what I said, whatever value is in the middle, that is the mean. So in this curve, the mean is 0. And then whatever the distance, whatever the distance is between these tick marks is the standard deviation. So here it's from 0 to 1, that's a distance of 1, so my standard deviation is 1. If we go back to lesson 14, page 3, this is our standard normal curve. Here's the areas.
Okay.
Yeah, okay. I don't expect you to memorize this. Number 4, let's find the probabilities given below and shade the respective region of the graph. This is a really good thing to be doing even if you're not asked to do it, because it helps you visualize the amount of area you're getting. In the next step, we're going to start using our calculator, and it's important to be able to recognize whether what the calculator spits out is reasonable or not. So it's always good to have an idea for what that looks like. I just need more room, so I'm going to erase this. But again, all of these bits that I'm doing here are about the empirical rule. Okay, so we're going to find the probability that z is between -1 and 1. And remember, the probability equals the area, which is why I started out writing the probability between -1 and 1. That's this region here. Okay, so we can shade that. That's 34 plus 34, which is 68%. Okay, but remember, probability, I have to write it in terms of a decimal. I write this in terms of percentages because it's easier for me to remember, but the answer here is 0.68. Okay, now let's do the next one. The probability that z is between -2 and 2. So I'm looking for that. So again, I'm going to shade this region that's going from -2 to 2, and we can color that in. That's all of this. So you see we have some overlap. So we could do this a little bit of a shortcut way. We know that green bit is 68, so we could just add that 13.5 twice. So here we have 68% plus 13.5 plus 13.5, which is 95%, or 0.95. Then to do that third bit, we're asked to find the probability that z is between -3 and 3. Okay, so what we're looking at here, -3 to 3, and again, that's including the orange, which we know is 95%, plus those two little added bits, the 2.35 plus the 2.35, which is 99.7%. So that probability is 0.997. This right here is the empirical rule, okay, that any piece of any data that is within plus or minus 1 standard deviation, or we say between 1 standard deviation, is 68% of the data. Always. If it's a normal curve, within 1 standard deviation is 68% of the data. Within 2 standard deviations is 95% of the data. And within 3 standard deviations is 99.7% of the data. And that tracks because if you look at this remaining bit, there's 2 of these. So 0.15% plus 0.15% is 0.3%. That's not a decimal, that's a percent. And here I got 99.7% plus 0.3% is 100%. While we're here, I will remind you of what things are considered unusual. That's that marker of 2. If you are more than 2 standard deviations on either side of the mean, that's how we determine if something is unusual. And that's because you see how little area there is, or how little of a probability we are likely to get anything out here. That's actually 2.5% likely to be above this region and 2.5% likely to be below that region. Again, this is a topic that's going to be coming back again and again and again. So the sooner you feel comfortable with it, the easier off you're going to be. So remember, I'm around before and after class for questions. We're going to do example 4 now. All right, so I have a normal distribution with a mean of 18 and a standard deviation of 3. So the first thing I'm asked to do is use my graph to label the x-scores and the z-scores and x-values, along with finding the median and the standard deviation. Okay, now look at here. I'm told the mean and the standard deviation. That information I'm always going to be able to get from the narrative. Okay, we're not at the point where we're calculating these anymore like we did in Unit 1 where we were putting everything in L1 and L2 and using one variable statistics. We're not doing that anymore. I'll always be giving you that information from here on in. I want to figure out the mean, and I'm going to use two different variables, colors. I'm going to use blue for the x values, brown for the z-scores, just so I can keep them straight. And you see how I labeled them here as well, so I can see which is which. And I would suggest you do something like that as well, so you can keep them straight. You could start with either one you want. I'm going to start with the z-scores, because that's what we just did. So we have 0, 1, 2, 3, -1, -2, -3. And remember, the z-scores tell us how many standard deviations we are from the mean, where the positive z-score means you are above the mean, and the negative z-scores means you're below the mean. The numerical value tells you how many you are above or below the mean. You see we've got a 2 here and a 2 here, and they're both 2 away from the mean. But this is negative, which tells you it's below the mean, and this one's positive, which tells you it's above the mean. So to figure out the x values, again, I'm going to put the mean in the middle, and my standard deviation is 3, which means the x value for here is going to be 1 standard deviation more than the mean. So that is a +3. So, and then from there, I'm going to add another 3, and there, I'm going to add another 3. Okay, so 18 plus 3 is 21. 21 plus 3, 4 plus 3 is 27. So you see here, to get this 27, we added 3 times. And that's why we get a z-score of 3. Now you try it on your paper with the left ones. Okay, and I'm not going to lie, for some of these I do have to bust out the calculator, especially when there's decimals involved. Math is hard for me too sometimes, folks. Don't take it personally. Okay, now we're doing the same thing except we're going below average. So that means we're going to be subtracting. So same idea, except it's -3, -3, -3. So I wind up with a 15, 12, and a 9. Okay, anyone get anything different? Anyone unsure on how I did that? And I always like to label the middle, the mean. I like to put the mu there, just for kind of good measure. So let's go into 17. Let's figure out what z-score corresponds to the given x value. And we're going to be doing this going forward, a number of we're going to be doing this a lot, is what I'm trying to say. Okay, so what I would always suggest is you use your graph to make an educated guess. You have this graph here. Take advantage of it. Okay, we have a formula we can use, but the fact is if you put that formula in your calculator incorrectly, you'll get the wrong value, and it's really important for you to have a sense on whether that value seems completely outrageous or if it seems reasonable. Okay, and you'll notice on my notes, I tend to put a little check to say, yeah, that looks reasonable. And I also write down what my guess is every time. Okay, so the first one I'm finding x is 21. Okay, so I'm looking over at my graph here, finding 21, and sure enough, you see 21 corresponds to the z value of 1. So I actually get that one for free. I'm going to write guess, but I know that it's z equals 1. Okay, but up above I was given the formula. So I'm actually going to use the formula to practice to make sure I know how to put it in my calculator correctly. Up above I have these conversion formulas. From z-scores to x values is here. Okay, so I've done the algebra for you. It's the same formula. We just solved it for x, which you may remember from algebra class. From x values to z-scores, we're using this formula here. And notice this note here, what you have to do to put it in your calculator. What's very important, we put parentheses around that subtraction in our calculator to make sure that we do this math first and then divide by that standard deviation. You may remember that being called the order of operations. To calculate this, I have z equals x, which is 21, minus the mean, which is 18, all over the standard deviation, which is 3. If we put this in our calculator, we would have to put parentheses around it. And the way you can remember this formula, the way I do, is that if the value is bigger than the mean, I get a positive z-score. So that's how I know that 21 comes first, because I know I have to get a positive number out of here. The other thing I can use to help me figure it out is this 21 is bigger than 18, which means I know I'm going to get a positive z-score. So if you do that math, you see 21 minus 18 is 3. 3 divided by 3 is 1. Okay, or you could put all of that in your calculator, but remember, use those parentheses. Okay, so let's do x equals 14. This is less than 18. And I'm choosing 18 because that's the mean. Remember, that's the whole key, is the z-score is telling you, is it above average or below average? So this is less than 18, so I know I should get a negative z-score. And again, that's just a quick check to make sure my calculator is spitting out the right value. Now use the graph and look at what your guess is going to be. 14. Well, 14 is somewhere in here. Would you agree? Somewhere between -1 and -2. So I'm going to guess -1.5. You know, your guess doesn't have to be great. It's probably not going to be perfect, but just start with something. Okay, so now we put this in our calculator, and that's going to be 14 minus 18 divided by 3. All right, so I put this in your calculator, and did you get -1.33? Hopefully the answer to that question is yes. And you see that tracks, right? We do the same thing with x equals 23. Again, we know it's bigger than 18, so we know it's going to be positive. Use our graph to make a guess. Let's see, 23 is somewhere between +1 and +2. I'm going to guess 1.5 and put it in my calculator to figure it out exactly. 23 minus 18. All over 3. What do you get? 1.7? And that tracks. This empirical rule is an approximation. It's not exactly 68 or 95 or 99.7, but it is really, really close. If we were to put these in our calculator, we're not going to get 0.68 exactly. We're going to get something very close to it, though. We just use the empirical rule as a way to get an estimate that we can easily calculate in our heads, or by looking at this graphic here. It's not exact, but it gives us a way to not have to have a calculator. Let's go to example 7. Here we go. Our calculator functions are on page 3. And remember, before we used binom CDF to find the cumulative probability for a binomial distribution. Now we have a normal distribution, so we're using normal CDF. And remember that C in the CDF stands for cumulative. Oh, okay, this is cumulative. We're never going to use the normal PDF in the calculator. That's not for our purposes. That's for something more sinister. No, actually. Just for other stuff. So we're using normal CDF. What we're putting in is the lowest number, comma. Again, those of you with older calculators, you know who you are. You'll have to enter in those commas. Uppermost number, the mean, and the standard deviation. Now, I want to make sure to note these two things. When we're finding x bigger than some number, we're going to use 99999 or some very large number. In the videos, they often use 1e to the 99. We're not trying to get that complicated. You can if you want to, by all means. You'll get the same exact answer. Similarly, for the lower bound, if we're finding x less than some number. In the videos, they'll be using -1e to the 99. I don't use that for two reasons. First of all, some calculators give an error if you use this number. I haven't figured out which ones, because the TI-84 has like a dozen different versions, if not even 20 different versions. But what we do know is the lower bound for everything is 0. Remember, we were talking about that with the last lesson. The smallest number of anything that we're going to be talking about with these continuous variables, all these continuous variables we're dealing with end at 0. Okay, so we can always, 0 works. We can always use 0. There are some circumstances where the negatives make sense, but for our purposes of these continuous variables, weight, height, those kinds of things always end at 0. So I'm just using 0, just so you know. So let's do this example here. We have a normal distribution with a mean of 50 and a standard deviation of 4. Okay, we want to label the axis with z-scores and x values. That's where we're always going to start out. If you see me giving you this curve, just know this is going to be the first instructions. Okay, so we can do this. The mean is 50. Standard deviation is 4. And I like to put this on the side even if I don't have a normal curve, because it just makes the calculations a lot easier because I'm going to be using them a lot. Okay, so I'm going to do x, then I'm going to figure out z. I'm going to start with x this time. So x is 50. And again, going to the right, I am adding 4 each time. And again, this continues beyond 3 standard deviations is just so unlikely that we stop at 3. 54, 58, 62. Going back to the middle. Doing the same thing, except with subtraction. -4, -4, -4. So we're going to have 46, 42, and 38. Okay, now on to the z's, which are definitely a little bit easier, I think. 0 in the middle, 1, 2, 3. Go back to the mean. -1, -2, -3. So now we're going to find the probabilities of getting a value that is between 42 and 50. So between 42 and 50 is here. You see how we could use the empirical rule to figure that out. We know that this first region here, we know this is 34%, and we know this is 13.5% from the empirical rule. But again, remember that empirical rule is an approximation. So if we want to figure it out exactly, we have to use our calculator. So from the empirical rule, we get approximately 13.5 plus 34. This will give us a ballpark, which is helpful to know if we put everything in our calculator correctly. 47.5% or 0.475. Okay, so now let's figure it out exactly. Now, what's nice about this is I have my two values here, and that tells me the lower, the upper values. Remember, because it goes low value, comma, or lower or leftmost value, upper or rightmost value, then the mean, then the standard deviation. Okay, so my lower value is 42, my upper value is 50. I will always be given those right there. Then my mean is 50. My standard deviation is 4. Okay, before we put that in our calculator, let's just do that next one too, and then we can just do them back to back. Okay, so now let's find the probability that get a value between 45 and 52. This is where we definitely need the calculator. 45 and 52 are not on my standard deviation lines. This area here, if you look at this, this is not symmetric. This is not like a square where if I cut it in half, I know the area is exactly half. If I cut this in half down the middle, it's not going to be exactly half. I'm not going to get a 17 and a 17% because one's definitely bigger than the other. And that's true for all of these. I can't cut these in half or thirds. The only way beyond the empirical rule to find any values that are not down here, or to find the exact probability, I have to use the calculator. For this next one, I'm asked to find the probability between 45 and 52. That's something like that. My leftmost number, again, I get those for free here because this is a 45 and this is a 52. So that's 45, comma, 52, comma, same mean, same standard deviation. All right, let's use the calculator. And again, we're at second vars, and then you see number 2 is normal CDF. The lower bound is 42. We're going to do part A first. Upper bound is 50. Mean is 50. Standard deviation is 4. Enter. And again, those of you without that menu, you should have something that looks like this. I'm going to hit enter one more time. And our guess with the empirical rule is 0.475, and our actual is 0.477. So you see the empirical rule is pretty close. It's a pretty close estimate, but if we want it exactly, we use the calculator. Now let's do the same thing for the next one. Remember, we can put second enter, and that brings it back, and I can change any of these values. Just use the arrow over the values you want, and just write right on top of them. So instead now I've got 45. I can either arrow over or just use the comma again, 45 and 52, and enter. And I get 0.586. Be careful with your rounding. And look at the chunk that we highlighted. Does 0.586 make sense? If that middle hump is 68%, that we would get something a little less than 68% seems pretty reasonable. Let's go on to number 26. I'm going to skip 25 because we just did that. So we want to find an X value corresponding to the Z-score. So earlier we were given the X value and we found the Z-score, but in this one we were given the Z-score, we want to find the X value. Okay, but again, use that graph that you have. Okay, so use this graph we have to get a ballpark estimate, and that tells us if it's reasonable or not. So we have a Z-score of negative 2.4. That's going to be somewhere in here. So we expect maybe a 40 for an X value. One thing I know for sure is it's negative, so it's less than 50, and my guess is 40. For a Z-score of 1.7, this is positive, so it's bigger than 50, and my guess, let's see, 1.7 is pretty close to 2, but a little less than 2. So I'm going to guess, I don't know, 56, 57? I'm going to go for 57. Okay, again, it's just a ballpark, just to make sure I'm doing my math correctly. Okay, so to calculate it, my X value, that formula I wrote right here for us. And again, if you want to double check it, practice your algebra, you can solve this equation for X because that's how we got this equation. Although in my algebra experience, that's one of the parts that people dislike the most in algebra. Okay, so we're figuring out X equals the mean, which is 50, plus the z-score, which is negative 2.4, times the standard deviation, which is 4. Okay, so there's two ways we can do this, and I'm going to show you on our calculator in a minute. Let's write the formula for the z-score of 1.7, and again, we can do those simultaneously on the calculator. Okay, so again, it's 50 plus 1.7 times standard deviation, which is 4. Now be careful with this negative. I can either write it like that with a negative 2.4, or I can write it as 50 minus 2.4 times 4. And remember, these parentheses, this means times. When things have parentheses or when two variables are written next to each other, the operation is times. So you can also write it as a asterisk like that, if that makes more sense for you, or an X. But I don't like to use X because there's an X right here. So you see how that X makes it a little bit confusing? That's why in my notes you'll see a little star like that instead of the times. Put that. Okay, so here we're doing 50. We can do plus. If you wind up doing a plus, and then you have to use the minus sign, which is here, not negative. This one is negative, addition, subtraction, times, divide. This means negative 2.4 times 4. Okay, so I get a 40.4. So you see my guess was actually pretty close. Okay, we could do this the other way, 50 minus 2.4 times 4, and you'll see we get the same exact answer. Now do the next one, part B, 50 plus 1.7 times 4, and that's 56.8, which we guessed 57, so it was pretty good. What we use those z-scores for are to compare apples and oranges, ACT and SAT, and that's what example 8 is asking you to do. You're given different scores for the ACT and SAT. Convert those scores, those are X values, convert them to Z scores, and then you can compare who did better. So we're working on examples 8 and 9. Curly is over here next to my desk staring at me, wanting me to scratch his belly.
Very big cat.
Okay.
Whoa, whoa. How much? 25 pounds?
Yeah. Look at that
Really?
belly. How would you not love to rub that belly? All right, so you've had a little more practice now with finding the probability distribution with using the normal CDF and finding the X value given Z and Z value given X. If you want more detailed information about this standard normal distribution on lesson 14, this is the important characteristics. This would be a great thing to print out and put on your little cheat sheet that you have. And again, I would suggest that you have a page specifically dedicated to the calculator functions. Well, let's go back to the one we're actually doing now, lesson 15. Okay, so you're comparing the scores. First one, hopefully you found that the ACT score of 38 was better than the SAT score of 1560. And essentially, test A was the SAT, test B was the ACT. Okay, and then on 28, again, the ACT score was worse because you see they're both below average, they're both minuses, but this one is further away from the average, so that's how you know this one is worse. Once we have z-scores for both of them, we can look at them on the same curve. The SAT and the ACT scores have different curves, but the z-score only has one curve, and that's where we can go back up to use that curve we did in example 1. And then for these, I would also suggest you check to make sure that it's reasonable, that it matches the graph. You know this area is 34%. We could have used the empirical rule, but using the calculator, you can see it's slightly more than 34%, 34.1, but you see that's why we just say, call it 34 because it's close enough. Check to make sure it's reasonable. This is the only one where the empirical rule is exact, that half, because remember that peak is the median, so you know anything below is half. So hopefully you got these same answers, and remember these answers are on Canvas on the pre-class assignment, and if you have any questions or we're still a little bit confused on something, stick around. I'm here for the next 20 minutes. Other than that, it's good to see all of you all. I hope you survived the power outages okay. Have a good afternoon.